Hey, today we're going to talk about how we could basically adjust the activation energy for a chemical reaction. So before we do that, you're going to need to get out your reference tables because you should always have your reference tables when you're watching one of these videos. Now, what we learned in the last video in 6.2, we have the potential energy of the reactants and the potential energy of the products. We have the reaction coordinates or the reaction progress, and then we have the potential energy on the side. Now, basically, if we look right here, potential energy of the reactants, the delta H of the reactants is 5 kilojoules per mole, and the delta H of the products is 1 kilojoule per mole. Now what we're going to notice is the heat of a reaction, or the enthalpy, that's a new word, enthalpy, which is another word for heat of reaction. The enthalpy is 1 minus 5, which is -4 kilojoules per mole. So let's pay attention to that. In fact, I'm going to put that up on the top. -4 kilojoules per mole. Because I'm going to get rid of this stuff and I'm going to show you something right now. So we know how to calculate the heat of reaction, but let's think back to the analogy that I told you. If a person were pushing a big giant boulder, ball, whatever they wanted to push, up to the top of the hill to get it to roll down the hill. This right here is the activation energy, the amount of energy it takes to start the reaction. Now, if I gave this person a shovel, it would make their job easier. So they take their shovel, and let's just say they start by digging a little hole out like this, and then they dig it out. Pretty soon, by the time they're all dug out, this path that the ball has to go is actually much smaller. So in other words, the activation energy went from 3 kilojoules. Now the activation energy is down to 1 kilojoule per mole. I'm going to estimate it's 1. So basically what happened is I didn't change the overall reaction. We still have 1 here, we still have 5 here, a difference of -4. This is still an exothermic reaction. All that I did was I changed the pathway for this person. Instead of going all the way to the top of the hill and rolling it all the way down, they just have to go up this little tiny incline in order to get the ball rolling. This right here, what I just did, is an analogy for what we call a catalyst. A catalyst, basically what it does is it lowers the activation energy by providing an alternate pathway for the reaction to go. Now we see catalysts all the time. In fact, we have thousands, even millions of catalysts in our body called enzymes. Every reaction that occurs in our body, from digestion to reproduction, involves enzymes. And these enzymes are catalysts. They're biological catalysts. Mostly biological, scissors and glue. And what they do is they're going to speed up reactions by providing an alternate pathway. A reaction that would normally take maybe 10 hours to take now takes 5 minutes or something like that. That's an example. One other thing is these catalysts are not consumed by the reaction. So they'll do their job. They'll allow the reaction to have an alternate pathway, and then they'll go back and they'll help out another part of the reaction. So they just keep going, and they're reused. They're not consumed in the reaction. They're not regenerated in the reaction. They're reused. So remember that. Keep that in mind. So basically, to summarize, all you really need to know is that a catalyst lowers the activation energy by providing an alternate pathway. Paractus problems. Peace.